Okay, welcome today to the characteristic classes lecture course. Today I want to use these characteristic classes to construct numerical invariants of manifolds and this is about Chern and Pontryagin numbers. So let me start with the Chern numbers. So we consider compact complex manifolds. So let M be a complex manifold. Let's call the complex dimension N. So the real dimension is 2n. Then we have a canonical vector bundle, namely the tangent bundle. Tangent bundle then is a complex bundle of rank n. So this is a vect MC bundle on M. And so it has a Chern class. And out of this Chern class, we can now produce numbers. How can we do that? Well, we can integrate over the manifold or evaluate against the fundamental cycle if you are a topologist, since it's a compact manifold. And there's not just one way to do it. In order to integrate something over the manifold and give us a non-zero number, we need to have a form whose degree is exactly equal to the dimension of this manifold. And for this, we can take components of the Chern class, combine them together in such a way that we get the correct degree. And we do it in all those ways in which it is possible. So this gives rise to the following definition. For any numbers I1 up to IR, natural numbers, non-zero, which add up to dimension. So the following number, let's take the Chern classes with these degrees. So C1 of the tangent bundle and multiply them. Now, what's the degree? The Chern class has degree 2i1 up to 2ir. So since this adds up to n, we get something of degree 2n. And 2n is the real dimension of the manifold. So we can integrate this over the manifold. And get a number, a real number. And in fact it's an integer, because we have seen without proof that these Chern classes are actually integral cohomology classes. So if I integrate them against fundamentals, I get an integer. That will not be terribly important to us, but let's note it here. So such a number is called a Chern number of M. So these are the Chern numbers. So I split my dimension in all possible ways, write it in such a partition as a sum of integers, so that the corresponding product of Chern classes gives me the right degree, and integrate them and get a number. These are the Chern numbers. Okay, good. So let's look at some examples. First example is our standard example, CPN. We have computed the Chern class of CPN, so the Chern class, or rather the Chern class of the tangent bundle of CPN, has been computed and was given as 1 plus a to the n plus first power.
Mit our convention, I'm just reduced to this one.
So I want to make the convention such that if I evaluate this guy against the fundamental cycle, I get plus 1. Of course, in the case that n is even, this makes no difference. So if we use the convention with a minus, that's also fine. Doesn't matter really.
Before we use it, we use that.
Okay. Doesn't matter. So then, okay. So then ith Chern class will then be what? N plus 1 choose I times minus a to the ith power. Okay. So these are the Chern classes, and now if I look at this expression, then I see that the Chern number of CPN gives me, well, I have these coefficients in front, so this will be n plus 1 choose I1 all the way up to n plus 1 choose IR. And then I'm left with minus I2 minus a to n, because the I is somehow to n. Okay, and good. So we have that, and so this has to be integrated. And so this gives me minus 1 to the n times n plus 1, choosing I1, etc. So these are the Chern numbers. And now, when we look at the special case, namely n equals 2. And in this case, well, which are the Chern classes, or which are the possibilities? We can either take 1i and set it equal to 2. So this would give me C2, GC2 integrated over C2, which is then, well, 3 choose 2, right? And this is 3. And the other possibility is to split the number 2 into 1 plus 1. So that will give me the C1 times C1. And so this gives me 3 choose 1 times 3 choose 1, according to this formula, which is 3 times 3, which is 9. So these are the two Chern numbers of CP2. Okay, and let's look at another example. An example which we had studied on the exercises in the past, namely the K3 surface, or more specifically the Fermi surface. So let me recall this for everybody. So what is the Fermi surface? So M is equal to the hypersurface of CP3 given by a polynomial equation, and the polynomial is F. And the polynomial that we are looking at is a fourth order polynomial. It's a homogeneous polynomial of degree 4. And now this variety corresponding with this polynomial v of f is by definition the set of all those lines in CP3. The line is given as C times Z, where Z is an element in C4. So that whole thing will be contained in CP3. So it will be lines in C4, and it's the lines that satisfy this equation. And of course, Z is not equal to 0, otherwise it wouldn't spread a lot. So this is the Z, and this is called the Fermi surface. It's an example of a K3 surface. So compare exercise 3 on sheet 8. And in this exercise, all of us computed the Chern class of this Fermi surface. So let me just recall the result. So namely, if you call the embedding of the Fermi surface into CP3 by J, then we can look at the corresponding, so we can take this generator of the cohomology of CP3 and pull it back to the surface and call this a twiddle. And now, so that's an element in the second cohomology of the Fermi surface. And now the whole Chern classes and everything will be expressed in terms of this a twiddle. There was a general formula that we proved in this exercise. Namely, the Chern class the surface is given as some from J equals 0 to 2, since it's two-dimensional, and here we have n plus 1, so 3, the dimension of that guy plus 1, which will give me 4, which is J, minus a twiddle to the Jth power, times, and then there's another term, sum, again from J equals 0 to 2, and then we have 4 to the, what do we call this, L, 4 to the L times a twiddle to the L. So this 4 is a different one than this 4. So there was a general formula for hypersurfaces of this kind, where CP3 can be replaced by an arbitrary dimension n, and this equation can be replaced by an arbitrary homogeneous equation of degree k. Now this 4 is n plus 1, so it's this number plus 1, while this 4 is the degree of the surface of this equation. Alright, anyway, so we have this formula, and so we don't have to sum higher than 2, because the V of f is something 4-dimensional. It's a complex hypersurface in CP3, so it's complex 2-dimensional, a real 4-dimensional, and this has degree 2, so at most the second power enters the game. Anything else has too high degree. So we can just compute this in this particular case. So let's see what we get. J equals 0 gives me 4 choose 0, which is 1, times this to the 0th power, so this gives me 1. J equals 1 gives 4 to choose 1, which is 4, times minus a to the first power, a2. And then we have J equals 2, which is 4 choose 2, which is 6. And then we have the second power. So that's the first sum. And here we have very good, so this gives me 1 plus 4 a twiddle plus 16 a twiddle squared. Right? So that's what we get. So I hope I did not mess with the signs of the a twiddle here. but it won't make a difference anyway. So we get, let's multiply it, 1 times 1 is 1. Now the linear terms in a twiddle is 1 times 4 plus 1 times minus 4, so this cancels, so there's no a twiddle term. And now the squared terms, so I have 1 times 16. I have 1 times 6. And I also have minus 4 times 4, which gives me minus 16, right? So that's what we get, and I don't need the higher powers because they will be plus 0. Okay, so I have 1 plus 6 a twiddle squared. So that's the Chern class. And so what are the possible non-zero Chern numbers? How many are there? How many non-zero Chern numbers? So in case of CP2 it was 2, right? It was these two.
Only one.
Which one? This one or that one?
The first one.
First one. Okay, let's see. C2 of T, CP. Not CP, sorry. F integrated over F. So what do we get? Alright, so that is 6 times a twiddle integrated over the fundamental cycle over the manifold. Now we have to know what this integral gives. In case of CPN it gives us 1, but in this case it gives us actually 4. It gives us, it's exactly given by the degree of this polynomial. So what we have in the F is 24. While the other one, as you already noticed, so this one, since C1 is 0, this gives me 0. So these are the Chern numbers of my Fermi surface. Good. Now what can I do with these Fermi surfaces? Well, only one remark that we can make is that if two manifolds are compact, or complex manifolds, are biholomorphic to each other, then they must have the same Chern numbers. So if M and N are biholomorphic, meaning there is diffeomorphism between them, which is complex, whose differential is complex linear. So that's just basically diffeomorphic as complex manifolds. Then all Chern numbers agree. And why? Well, namely, so suppose we have such a biholomorphism. So F is a diffeomorphism from N to N. Which is biholomorphic, so holomorphic in each direction, meaning the differential respects the complex structure of the tension bundle, such that dF is C-linear. Then, let's see, if we compute the, let's say, the Chern numbers, so let me write it like so. So this is my tuple numbers, and then I call C of this tuple. So that is then this product of Chern classes of a tension bundle. corresponding expression here, and I do this with m and integrate over m. Well then, since this is C-linear, it's also an isomorphism between the fibers, so actually this means that this tangent bundle here is the same as the pullback tangent bundle of m, as a pullback as a complex vector bundle. And now Chern classes are natural, so I can pull out this pullback, and the pullback also computes with multiplication, so that is the same thing as f star of Ci of Tn. And this is the same as Ci of Tn integrated over the image under this map of M, which is A. If you write this as an integral, this is the diffeomorphism invariant of integrals of different forms. Okay, so that means if I have two manifolds which are biholomorphically equivalent, which are biholomorphic to each other, then they must have the same Chern numbers. Now here we have computed the Chern numbers both of CP2 and of the Fermi surface, and it has turned out that they differ, right? So here we have 0 and 24, while here we have 3 and 9. So they differ, so therefore they cannot be biholomorphic. This example. Example, CP2 and Fermi surface are really different. Biholomorphic to one another. So this is these are invariants of manifolds which can be used to distinguish manifolds, in this case complex manifolds. Okay.
I have maybe a little bit of an off-topic question, but what exactly is it?
Okay. Well, I'm not going to tell. Yeah? So this is a particular surface, which is called the Fermi surface. And this is an example of a K3 surface. There's an algebraic geometric definition of it, but in fact, as differentiable manifolds, all K3 surfaces are the same. So just think of this as, since we will be looking at, so it's not that they all are same, that they're all biholomorphic, that's not the case, but they're all diffeomorphic. And the classification of K3 surfaces from the algebraic geometric point of view or from the complex point of view is an interesting and much studied topic. So but this goes far beyond what we want to do. So we will be mostly looking at these things as differentiable manifolds, and from that point of view, this is the K3 surface, if you wish, or one possible description of the K3 surface. All right. So I mean, we have seen that as complex manifolds, CP2 and this Fermi surface are not the same. They could still be diffeomorphic a priori, right? So this applies only, this Chern numbers argument applies only if they are really biholomorphic. Then they have the same Chern numbers. In order to see that they are not even diffeomorphic, we have to look at Pontryagin numbers. So let's do that. So now let M be an oriented, compact, differentiable manifold. And in in order to get something non-trivial, using Pontryagin classes, I have to assume that the dimension is divisible by 4. So dimension, now this is of course the real dimension, there is no complex structure here, is divisible by 4. That is minus 4k. Otherwise, I will not get anything non-zero. Now the definition is, whenever I take a partition of k, for any numbers I1 up to IR in n which now add up to k, so 1/4 of the dimension. For any such numbers, the number. Now I play the same game with the Pontryagin classes. So I take pi I of the tangent bundle of n and integrate it over n. This again gives me an integer where, so this is called Pontryagin number. Where this pi, this says for Chern classes, this is the product of the corresponding parts of the Pontryagin class. Just as for Chern class. Okay, good. Erasers here. So let's look at our examples again. M equals CTN. And actually this works only for even n, right? Because only then the real dimension is divisible by 4. And but anyway, so what's the Pontryagin class of the tangent bundle? Now considered as a real vector bundle. Oh, by the way, here I have assumed that this is an oriented manifold. In fact, for the Pontryagin classes, I don't need that. Right? So the Pontryagin classes don't require an orientation of the bundle which I'm taking. The orientation is only needed for the fundamental cycles, for the integration. If you want to integrate a form on a manifold, the manifold must carry that orientation. Right? So this orientation that I have assumed here has nothing to do with the Pontryagin classes, really. It's only to get this fundamental cycle, to get sense of the integration. Right, and so what's the Pontryagin class? So now the sign should be a plus in any case, this one. And well, so that is sum n plus 1 choose j, summing from j equals 0 to n on 2 times a to j, right? That's the Pontryagin class, what we have computed earlier. And so the corresponding Pontryagin numbers are now just given as n plus 1 choose r1 times n plus 1 choose ir times this guy. So this goes all the way up to 2n. So only for n even, this will give me a to the n. Otherwise, it gives me a to the n minus 1, which will. So for n even, if n is odd, we get 0 anyway. So this is 1, this guy. So we have, so that's 1. this product of equations. Looks like the same result up to a sign as for Chern numbers, but that's not quite the case. Why? I have erased the Chern numbers, but for the Chern numbers we also have exactly these products. Remember? Up to the sign minus 1 to the nth power, which would be 1 for even n here. But why is it not the same?
The numbers now add up to k.
Exactly. Here the numbers add up to k, which is the dimension, which is
number 4.
Yeah, it's the complex dimension on 2, and for the Chern numbers it was the complex dimension. So that's why we have less Pontryagin numbers than we have Chern numbers. In case of n equals 2, let's look at the special case again. We have only one Pontryagin number, namely, then in this case we would have to sum up, so the k is equal to 1 now. So it's the only possibility is 1 equals 1 here. And so we have the first Pontryagin number, which is already of degree 4. So this one is then given by n plus 1, which is 3 on choose 1, which is 3. And let's look at the Fermi surface. Now, let's see. We still have the Chern class of the Fermi surface there. And what can we deduce? So this is the Chern class of the Fermi surface, meaning the tangent bundle of the Fermi surface considered as a complex vector bundle. And now we want to have the Pontryagin class of the Fermi surface, of the tangent bundle of the surface considered as a real bundle. Now, how do we get the Pontryagin class of the realification of a complex bundle? Remember, the Pontryagin class of a real bundle was essentially, up to some signs, it was the Chern class of the complexification of the real bundle. So what we do here in this case, we take the tangent bundle of the Fermi surface, which is complex, forget the complex structure and complexify again. And if we do that, the result that we will get is the original complex bundle plus its complex conjugate. So what we are interested in is the Chern class of the tangent bundle plus the complex conjugate, when I consider these as complex bundles. Alright, so this is the Chern class of the tangent bundle times the Chern class of the conjugate of the tangent bundle. Now, with this we have computed, this is 1 plus 6 a twiddle squared times conjugation missing. And now, what happens if to the Chern class if we conjugate a complex bundle? Not quite. The Chern class is real, but this doesn't mean that nothing happens, right? Yeah, exactly. So in this case, we don't have any odd parts. So then, in this case, you're right, nothing changes, yeah? Because there are no odd parts that change their signs. So I get a square here, indeed. And if you multiply this out, then I get 1 plus 2 times this guy, which is 12 a twiddle squared. And this is already the top dimension. A twiddle has degree 2, so this has degree 4, which is the dimension of the manifold. So there's no quartic term. Okay, so that is the Chern class of the bundle plus its conjugate. So from this, we can now read off the Pontryagin class. So what's the Pontryagin class now? class of the tangent bundle? Suggestion?
1 minus 12 times.
Yes, it's 1 minus 12. Because by convention, the Pontryagin class has the sign flips in odd modulo, so divided by 4 odd degrees. So we have 1 minus 12 base squared. And so we can now compute the corresponding Pontryagin number. By integrating that guy, first one, so this minus 12 field squared over this family surface. And what we get is minus 12 times, and the integration of a field squared, remember, gives is 4, because the degree of the equation is 4 times 4, so this is minus 28. That's what we get. So we see that the Pontryagin numbers, there is only one, of CP2 and of the family surface are also different. And this should tell us something about real differentiable or diffeomorphism types. And in fact, it does. And this is given by the following remark. So if there exists an orientation preserving diffeomorphism from n to n, then all Pontryagin numbers coincide. Same argument as before, except that instead of a biholomorphic diffeomorphism, we now look at an orientation diffeomorphism, which respects the structures that we have in this case, namely the tangent bundle of n pulls back to tangent bundle of m as an oriented real vector. So it's the same argument. So in particular, there is no such orientation preserving diffeomorphism between CP2 and the K3 surface. For example, no such diffeomorphism from CP2 to the family surface.
Are there diffeomorphic manifolds where there is no orientation preserving?
Yes. I mean, we'll come back to this in a moment.
And all biomorphisms are orientation preserving.
Yes, automatically. If you respect the complex structure, then you automatically respect the induced orientation. The orientation is induced by the complex structure. All right. So we have that, and now the Pontryagin numbers tell us a little bit more about our manifolds. So I want to correct this. Namely, that's the following proposition. Okay, so let M be an oriented compact manifold as before. Yeah, of dimension 4k. I don't really have to write this because I will give conditions under which all Pontryagin numbers vanish, and in the other dimensions they vanish anyway, so this result will still be true. So then, if there are two options, so if there is an orientation reversing diffeomorphism from the manifold to itself, if there exists an orientation reversing DPO from M to N, then all Pontryagin numbers vanish. There will be another sufficient criterion, a sufficient condition for vanishing, which I will write down in a moment. Let me first prove this case. Okay, so let's assume we have an orientation reverse in diffeomorphism from M to itself. So let F from M to M be an orientation reversing diffeom. Well, what will happen then? Since it's a diffeomorphism, the pullback of the tangent model of M is still the tangent model of M. And so there's no, regarded as real vector bundles without orientation, right? So we certainly have that, and therefore, if we look at the Pontryagin class, then this is the same as the Pontryagin class of that one. And by naturality, this is the same as the Pontryagin class. So, the Pontryagin, so the diffeomorphism pulls the Pontryagin class back to itself. And if we now look at the corresponding Pontryagin numbers, so we integrate over M. This is the same as back. And this is the same as a diffeomorphism invariance of the integral of differential forms over an oriented manifold as this fundamental cycle. And the fundamental cycle, since this is orientation reversing, now this is the same thing as the fundamental cycle with the opposite orientation. Right? So it's negative that one, so which gives me minus So this orientation reversing diffeomorphism doesn't do anything to the Pontryagin class, but it flips the orientation around. And this is why we get a minus sign for the Pontryagin numbers. So the Pontryagin numbers are equal to their negatives, and therefore they must vanish. So that's the proof of this case. And the second case would be if B, and this is when your manifold is the boundary of a bigger manifold. So if there exists an oriented manifold W with boundary, and the boundary is manifold M. So meaning that also the orientation on W induces the given orientation on M. So it's a manifold with boundary as an oriented manifold. And the boundary is to be taken with its induced orientation, which is our given oriented manifold M. Then all Pontryagin numbers must also vanish. If our manifold bounds, then the Pontryagin numbers must vanish. Put it quickly. Bounds as an oriented manifold. And why is that true? So let's see. Part B. I think this can go now. Okay, so assume that we have such a manifold W. Then let's write down one of these Pontryagin numbers. And let me write it as an integral using differential forms. So here it's a cohomology class, and here the PI is to be understood as a representing differential form. I'm not going to distinguish it in notation. It's clear from context, right? And so we have that. And now, okay, if we call the inclusion of the manifold M, which is the boundary W, into W by J, then what do we have? If I take the tangent bundle of W and pull it back, which means I pull it back to M, what do I get? I get the tangent bundle of M, but that doesn't have the correct rank, right? This has rank n plus 1, this has rank n, so it cannot be the same thing. But in fact, there is something missing here, namely the normal bundle to the boundary. And the normal bundle to the boundary is something trivial. It's a trivial rank 1 bundle. So let me have over this notation of epsilon to the k for the trivial bundle of rank k. Right, what we have picture is this. So this is my manifold W. Here we have the boundary, which is M. And if we restrict the tangent bundle to the boundary, then we get the tangent bundle of the boundary plus normal bundle. And the normal bundle is spanned by the exterior bundle, which trivializes the normal bundle. I mean, this does not require any orientation really. I just have the fact that I can distinguish between exterior and inward normal. So if I always take the exterior unit normal, then this trivializes the bundle. So that's why we have this. You can write it like so. So that's the normal bundle. And once we have that, we can conclude for the Pontryagin class of Tm, which we have in this equation up there. That's the same thing as the Pontryagin class by adding a trivial bundle, because here we have the product formula, but this is a trivial bundle, so Pontryagin class is 1. So this times 1 is this. And that's this guy. And by naturality, I can pull out the J star. Okay? So if I want to replace this by this equation, let's do that. And we have integral over M, and then we have J star of Pi of the tangent bundle of W. Okay. And now I use the Stokes theorem. So if I write this M, if I write this as the boundary of W instead, by the Stokes theorem, that's the same as the integral over W of the differential of this one. But forms representing cohomology classes are closed. So this integral is 0 and 0. So it's a consequence of the Stokes theorem. So if our manifold bounds, then the Pontryagin class, all Pontryagin numbers must vanish. All right. Good. So this in our examples, let's see what this tells us. We have computed the Pontryagin numbers of CPN as well as of the Fermi surface. So let's see what this proposition now tells us. So maybe I can erase this proof, right? So in the example of CPN, well, for n even, so we certainly have one Pontryagin number of CPN which is non-trivial, namely, if we look at the n on 2, so maximal degree here. So that is certainly, the other one's also non-trivial, but this certainly gives us n plus 1 choose n on 2, and that's not zero. So CPN has non-vanishing Pontryagin numbers. So therefore, by this proposition, A and B cannot hold. So that means, therefore, there is no orientation reversing diffusion from CPN to CPN, and also CPN does not bound. And there is no W oriented such that CPN is its boundary. Right? So compact and oriented study. All right, good. Now, how if n is odd? If n is odd, the proposition doesn't tell me anything, because for odd n, all Pontryagin numbers are zero. So I don't know. So what would we think? It does, for example, is there an orientation reversing diffeomorphism? Well, let's look at the simplest case that comes to our minds, namely n equals 1. N equals 1. What happens? For n equals 1, CP1 to CP1. CP1 is S2. Question, is there an orientation reversing diffeomorphism from S2 to S2? Namely, which one?
Antipodal map.
The antipodal map. Yes. So for n equals 1, there is such an orientation reversing diffeomorphism indeed. And for higher n's, odd, there's also one. Namely, look at this one. So the diffeomorphism, we have this diffeomorphism in all dimensions, CPN to CPN. And what does it do? It takes, so the elements of CPN are lines in Cn plus 1, right? And so I can take such a line and map it to its complex conjugate, which gives me a new line in Cn plus 1. So this diffeomorphism we have in all dimensions, but for odd n, this is orientation reversing. So this is orientation reversing for odd n. So we have to maybe think a little bit about why that's the case. Well, how do we see that? Yeah, how do we check that? We can look at this map in our standard complex coordinates. And so our complex coordinates are automatically positively oriented because the orientation is induced by the complex structure. And then we can see what this map does in our standard complex coordinates. So let's check that. And if I have an element z equals to z1 all the way up to zn, in one of our standard charts on CPN, how does the standard chart work? Well, we take the line which is spanned by a vector in Cn plus 1, where at some slot I insert a plus 1 here. So that is C times the line, say we start with that 1, at some point we get a 1, and then we continue all the way up to Cn. So this is how the standard chart works. That covers the whole domain of all those lines, consisting of those lines where this slot is non-zero. And now I apply this map, and I have to conjugate. So some constant times this vector. If I conjugate it, I get some constant, conjugate constant, times the conjugate vector. 1 conjugate is equal to 1, of course. I get this one. And in my, so this corresponds in my chart to the vector z squared, right? So in other words, in my chart, I just have conjugation. I mean, what else should it be? So it's just conjugation. And now, what does this do to the orientation? Well, in each complex line, which is a real plane, conjugation is orientation reversal. Right? It's reflection about the real axis. And so if I have n complex lines, this consists of n orientation flips. So if n is odd, this is really orientation reversing. Whereas if n is even, it's the orientation is preserved. So indeed, this discussion shows that everything is consistent. So for even n, we do not have any orientation reversing diffeomorphism from CPN to CPN. Whereas for odd n, we do. And here is one. And we were able to read this, showing that for odd n we do have it. It's just writing down this simple diffeomorphism. That's easy. But showing that for even n we do not have one, this requires this power of characteristic classes. All right. So much about CPN. Let's see. For B, so is there an oriented? So does it has CPN bound? For even n, it does not bound because of this proposition, right? We do have a non-trivial Pontryagin number, so it cannot bound. How about odd n's? Does CPN bound when n is odd? And well, if it does, I should just give you such a manifold value that doesn't show, right? And let's see if this is true. So for odd n, CPN bounds. Compact orienting manifold W. How do we see that? Well, so let me write n equals 2k minus 1. Yeah. And now we have the following map. CPN to a quaternionic projective space. And what is the map? So I take a line L, it's a complex line, in Cn plus 1, right? Which is equal to n C2k. And now I identify C2 with complex numbers, with quaternionic numbers. And both of them are just R4k. So that means I can map this complex line to the corresponding quaternionic line. So, so I take a vector out of this line, and I do not only take all complex multiples of it, but all quaternionic multiples of it. So I should write it like this. Here I have C times some element Z, I map it to H times the same unit set. So that's the map. So this lands me in a quaternionic line in HK, which is then this line form a quaternionic projective space. Okay, so we have this canonical map. So and this works only if n is odd. Now, what I'm claiming is that this map is actually a fiber bundle. So here is fiber bundle. And what is the fiber of it? If we have a quaternionic line, then the question is, what are all the complex lines that map to this quaternionic line? And yeah, what is this? If we fix a quaternionic line, what are all the complex lines mapping to this quaternionic line? These are all complex one-dimensional subspaces of this one-dimensional quaternionic space, which is a two-dimensional complex space. So I'm looking at all one-dimensional complex lines in a two-dimensional complex space. So the fiber is the lines, all complex lines in a C2. So that's a CP1. Yeah. Fiber bundle, blah blah blah, with fiber CP1. Model fiber CP1. Okay, so we have this map. Now, why is this useful? Well, CP1 is S2, as we know. And now, and here I'm a bit sloppy, but we'll tell you how to remove the sloppiness. So now here we have our quaternionic space, right? And here we have our complex projective space. And this is our fiber CP1 or S2. So that's the picture. And we have all these fibers which are S2. And now S2 bounds the ball. And so what we really do is we fill each fiber with a 3 ball. And this way we fill all of CPN. And this gives us a manifold whose boundary is CPN. Yeah, by filling each fiber with a ball. So this argument is sloppy in the sense that I can certainly do this filling at each fiber. S2 is bounds per ball. But you have to show that this filling of fibers can be done consistently along the basis, so that the union of all these fillings really gives you a manifold of dimension 2n+1. And in order to make this rigorous, what you do is you check that this fiber bundle, so if you have this fiber bundle, a priori, the structure group is the diffeomorphism group of S2 or of CP1. But you can choose your trivializations in such a way that the structure group reduces to SO3, acting in the standard way on S2. And when you have that, then you can directly extend to a ball bond, because the SO3, you just extend the action of SO3 on S2 to the action on 3 ball. So that's really the crucial observation. You have to find a system of local trivializations of this bundle such that the transition functions take their values not in arbitrary diffeomorphism of S2, but rather in elements in SO3. And this way you can make this precise. I'm not going to do that, it's not that important to us. I just wanted to mention it, so that indeed in in odd dimensions, in odd complex dimensions, CPM does bound, whereas in even dimensions it doesn't, because of the Pontryagin numbers. Okay. Is that clear? Yeah. And well, in this other example of the K3 surface, here is still a Pontryagin number, or a non-vanishing Pontryagin number on the K3 surface, or Fermi surface. And this tells us that also for the Fermi surface, there is no orientation preserving, orientation reversing. That's the wrong thing. Huh? There is no orientation reversing diffeomorphism, and also it does not bound. Because of this, there's not much anything else to say. So it applies also in that case. Good. And now let's recall the Euler number. So we also have the Euler class and the Euler number. There's only one Euler number, namely just integrating the Euler class over the tangent model to the manifold, and the result is then the Euler number, and it's the classical Euler number by the Chern-Gauss-Bonnet theorem. And in fact, the Euler number, this proposition that we have here is not true. So remark. So proposition does not hold if you replace the Pontryagin numbers by the Euler number. Are replaced by the Euler number. Namely, so what would it say? If it was true, it would say, well, if there's an orientation reversing diffeomorphism, then the Euler number must vanish. But that's not true. Who can give me a counterexample?
Sphere.
The sphere.
S2.
S2. Exactly. S2 is a counterexample, maybe more counterexamples. So we can certainly take this one, right? That's also a counterexample. Anything else?
I mean, kind of every-oriented surface besides the torus bounds and has non-vanishing.
So this is a counterexample to both, right?
Oh, okay.
So indeed, it bounds a ball, and there's this the antipodal map is orientation reversing. So that's good. It's a counterexample to both. And now you are saying, okay, there's surfaces other than the two sphere, namely, let's say, MG, which is a connected, oriented surface, compact surface of genus G. But the genus should not be, so it should not be the torus, so it should be not equal to 1. If it's 0, then it's the 2 sphere again, and if it's larger, then it's a higher genus surface. And the Euler number of such a surface is what?
2 minus 2 times G.
2 minus 2G. So if G is not 1, that's non-zero. These surfaces obviously bound because you can realize them in R3. And they separate something interior and exterior, so they bound the interior. And well, now how about this guy, this one?
You can realize them by gluing the polygon at the sides. And reverse that.
Okay.
I don't know.
Yeah, so let's leave this open. We have further counterexamples to affect both of them. We'll discuss them today. If you take Cp to some odd power, then we have seen this bounds, and it has an orientation reversing diffeomorphism. But the Euler number is what? Is 2k. Yeah, it's one more than the complex dimension. So lots of counterexamples actually, right? So the Euler number behaves completely different to the Pontryagin numbers. So that's the point I want to make. So these are counterexamples.
The surface, could we arrange the surface such that it's kind of symmetric, like some plane, and switch that plane? That would be...
Yeah, you can take an upper and a lower part, make it symmetric, and just flip. This would be orientation reversing. Good. So we have lots of counterexamples to both statements where the Euler number is not zero. Right? So but the Pontryagin numbers must be zero. Good. So that's this part. So then the next section, I want to discuss the Chern-Gauss-Bonnet theorem. I've stated it without proof, and we want to prove it. And to start, let's look at the following simple lemma. So let F be some bundle which has an Euler number, Euler class. So it should be an oriented Riemannian vector bundle. So the fibers are oriented Euclidean vector spaces of dimension, some dimension n. And then the statement is if there exists a smooth, actually continuous will suffice, a smooth section S of F, which is nowhere zero, so nowhere vanishing section, so with S of x not equal to 0 for all x in M, then Euler class of F vanishes. So that's a statement about the Euler class, not about the Euler number. So here we don't really actually need M to be compact. I'm not applying the Gauss-Bonnet theorem here. And so why is that? Proof. Well, why is it? If we have such a section, so given such a section, then at each point of the manifold, the multiples of S of x define a one-dimensional subspace of Fx. Then Lx to be defined as R times S of x in Fx. So that is a one-dimensional real subspace. And it's also oriented because so we just take the positive multiples of S in one direction and negative ones in the other direction. So this is actually an oriented real subvector space, one-dimensional. So that means our bundle F has this line bundle as a subvector bundle, and at each point we can split it into L and its orthogonal complement. And that's a splitting of our vector bundle F into two oriented real bundles with metric. So we start here with the Riemannian vector bundle. So then we have this club available, and we can restrict the Riemannian metric to both of these. And this, of course, also inherits an orientation, namely in such a way that the combined orientation here add up to a given orientation F. So that is a splitting of F into, yeah, that's an or equal 1, and this one or equal n minus 1 or bundle. And now take the Euler class F, and as we mentioned so earlier, the Euler class is also multiplicative with respect to direct sums. Look at that. But this is trivial. So the Euler class, the trivial bundle is 0. That's it. Good. Okay. Once we know the Gauss-Bonnet theorem, this tells us that all these manifolds that we have here as counterexamples, they all have non-trivial Euler number. So the Euler class of the tangent bundle must be non-trivial. And so the Euler class must be non-trivial. And therefore we cannot have such a section. Right? So example. And sections of the tangent bundle are just vector fields. So we are talking about nowhere vanishing vector fields. So the following manifolds do not have nowhere vanishing smooth or continuous vector fields. If you had a continuous nowhere vanishing vector field, you would also have a smooth nowhere vanishing vector field, because you could apply a modifier to it locally and just smoothen it. So I could replace this by continuous if I wanted. So I have these counterexamples, and indeed, so let's see. If the genus is equal to 1, so that's nothing but the 2 torus. And the 2 torus does have such a vector field, right? Could just take a vector field that goes around these circles. So in this case, you do have a nowhere vanishing vector field. In fact, the tangent bundle of T2 is trivial. So I have that. So there's good reason for this condition G not equal 1.
I have a question. This remark before actually there was this like kind of really implies what I asked last time, that like the Euler characteristic or Euler class is independent of the
Yeah, we saw this on the exercise sheet too, if you have taken a look at it.
yeah, but that didn't follow exactly.
No, it was just asked to give, there are examples of manifolds which have trivial Pontryagin class and non-trivial Euler class and vice versa. So they are simple examples.
Yeah.
So they are really independent. And also they behave differently fundamentally. If you switch the orientation, as we have seen, the Pontryagin numbers change sign, but the Euler number doesn't. And the reason is the Pontryagin classes do not depend on the orientation, only the fundamental cycle. While in the Euler case, both the Euler class and the fundamental cycle get a sign. And so this cancels, and this is why the Euler number does not depend on the orientation. So they are really quite different in their behavior. Okay. Yeah, good. And so that, this is another proof of the Harry-Ball theorem. We had the Harry-Ball theorem for S2, and we saw earlier using only Chern classes that the Harry-Ball theorem holds for S2, but now we see that it actually holds for all even-dimensional spheres and for all surfaces and also lots of other manifolds. So, right, so this implies the Harry-Ball theorem. Just to remind you. Okay. And then I will stop now for today, and next time then I start with the actual proof of the Gauss-Bonnet theorem, which will take a little bit of time. Thank you.